Okay, here's equation or sample problem 5.7. Given the following thermochemical equations, determine the enthalpy change for the reaction NO plus O turns to NO2. So this is a standard Hess's law type problem. And what we're going to do is we're going to combine the first three equations that are given to give us the fourth equation. And if we do that, we can then add the delta H's for those first three equations to give us delta H for the fourth reaction. Okay, standard type of problem. Now the issue here is that this is really a puzzle. Look at Hess's law problems as puzzles. And really you should look at all chemistry problems as puzzles, but this is definitely very much like a puzzle. What happens is if you add the first three equations together, you're not going to get the fourth equation. They have to be manipulated in some way, and that's the way the author has generated this particular problem. So you have to figure out how to manipulate them. So what I'm going to do is I'm going to show you how I would approach this problem. What I would do is I would try to manipulate those first three equations so that I get the fourth equation. So let me show you how I would approach it. The first thing I would do is I would write down the equation, and I'm going to call it equation 4. That's the one that we want. NO gas plus O gas turns to NO2 gas. And we want to know what delta H for that reaction is. I'll call it delta H4 because it's reaction 4. So here's what I'm going to do. I'm going to look at the first reactant in that substance, in that equation. The first reactant is NO gas. And I'm going to look to see if there are any of the three equations that have NO gas. Okay? So I'm looking at the chemical formula and the state of matter. Both the chemical formula and the state of matter have to be the same. So if you look at those three equations, you can see that the first equation has NO gas. So I found one. Equation 2, does it have NO gas? No. Equation 3, does it have NO gas? No. Only the first one does. So the next step I do is I look to see if the NO gas is on the same side as it is in equation 4. And if you look at it, it is. It's on the reactant side. Then I look to see if it's the same number of moles. Is the coefficient the same? And if you look at it, the coefficient is the same. It's 1. So that means that equation 1 is written in such a way that it gives me exactly what we want in terms of NO for equation 4. So for reaction 1, I'm just going to copy it. I'm going to make no changes whatsoever. And if we make no changes to the equation, then we make no changes to the delta H. So delta H1 is going to stay the same. It's negative 198.9. I'll leave the units off, but these are all in kilojoules per mole. Okay? The next thing I do is I look at the second reactant in equation 4. O as a gas. Not O2, not O3, but O. That's called atomic oxygen. And I look for all the equations, 1, 2, 3, that have O gas. And it turns out there's only one of them. It's the third one on the right. O2 gas turns into 2O gas. However, it's on the opposite side. It's a product in equation 3, but it's a reactant in equation 1. That tells me I have to reverse equation 3 to make it on the left side. We want it on the left side, equation 4. So I'm going to take equation 3, and I'm going to reverse it. But there's another change I have to make as well. The coefficients are not the same. Instead of being a 1, as it is in equation 4, it's a 2 in equation 3. So I have to multiply equation 3 by a half to make that coefficient a 1. So I'm making two changes to equation 3. I'm reversing it, which, by the way, if you reverse the equation, you change the sign of delta H. So it becomes a negative. and I'm going to multiply it by half so that the coefficient becomes a 1, and that means you have to multiply delta H by a half also. So we're going to end up with O turns to, now O2 was a 1, but I'm multiplying it by a half, so it becomes a half O2. And then delta H3 would be a half times negative 495, which is negative 247.5, right? We're making two changes. We're reversing it so that the O is on the reactant side, as it is in equation 4, and we're multiplying by a half so that it's the same coefficient, which is a 1. The coefficient should be a 1. Okay? Now I'm going to look at the third material in equation 4. It's NO2 is a product. NO2 is a product in that equation. It's also a product in equation 1, and we've already dealt with equation 1. We've already done that. So the question then is, what about equation 2? We haven't looked at it yet. Well, equation 2 pops in here for the following reason. We want the overall equation to be NO plus O turns to NO2. There's no O3 in there, right? But if you look at equation 1 has O3. So that O3 is going to pop up if we add equation 1, 2, and 3 together. So here's what we do. We try to figure out how to get rid of that O3. We haven't used equation 2. So what I'm going to do is I'm going to look at equation 2. It has O3 as a reactant. If I were to add equation 2 to equation 1, we'd have two O3s. But I don't want O3 at all because equation 4 doesn't have O3. So I'm going to reverse equation 2. If you reverse equation 2, that'll put O3 on the product side. And then when you add the three equations together, the O3 will cancel. So equation 2, 3 halves O2, 3 halves O2, is going to turn into O3. And so I'm reversing that one. So that means it's going to go from negative 142.3 to positive 142.3. Okay? So now here's the check. We're going to add equations 1 through 3 now that we've made these changes and see if we get equation 4. That's the puzzle aspect of this. We want to have NO plus O turns to NO2. So we have NO, that's good. O3s are going to cancel. They're on opposite sides, so they cancel. On the left side, we have one O and none on the right side, so O is there. But what about O2s? Let me remind us a little bit about algebra. If you have 1/2 x and you're going to add that to 1x, that would be 3/2 x, right? Because 1x is 2 over 2x, and 1/2 plus 2/2 is 3/2. Likewise, if I have 3x on one side and I have 3x on the other side, we can subtract 3x from both sides, and the x's are gone, right? So same thing here. If you have O2s on both sides, you can cancel them. So on the left side, we have 3/2 O2. On the right side, we have a half O2 and 2/2 O2. That's 3/2. So the O2s cancel. They're gone. And the O3s cancel. They're gone. So that leaves us overall with NO plus O gives us NO2. And that's exactly what we want. That's equation 4. So combining these forms of equations 1, 3, and 2, or 1, 2, and 3, should give us the right answer. So now we got to add the delta H's. We have negative 198.9. So I'm going to add 198.9, but it's a negative number. And we're going to add that to 247.5. But that's also a negative number. And then we're going to add that to 142.3, but that's a positive number, and you get negative 304.1. Kilojoules per mole. there's our answer. Okay? So like I said, it's a little puzzle, and you have to go through these puzzles and figure out what the delta H is for the desired equation. Okay? Remember, 2 points. If you reverse an equation, you have to change the sign of delta H. If you multiply an equation by some constant, half or 2, you have to multiply the delta H by that value. You can then check to see if they add up to give you the overall equation. If they do, then you can add the delta H's.